Well, hello friends. Welcome back to OS haxx0ring. Today we are going to play around with a kernel bug that I found in Serenity OS, and we're going to try to turn it into an arbitrary read exploit for the kernel. So let me start by showing you the problem. So it's an issue with the profiling system that we have built into Serenity OS, which normally allows you to capture regular samples of what a program is doing at a regular interval and view them in a profile GUI. You can also capture certain interesting events like allocations, freeze, stuff like that. And if I capture something using the profile command, let me just run ls and capture that. Probably not super interesting. Actually, I have to do profile-c ls. Okay, there we go. So that gives us a ls37.profile. So that's just the name of the command and the PID. And we can open that up and view it in Profiler, which is our GUI that allows you to look at individual samples and so on. So the real problem here that I noticed is that we are capturing all of these user space stack frames in each of the profile samples, but we are also capturing kernel stack frames, and we can't symbolicate those and show you like which kernel function is each frame here, but we do still have the kernel addresses, and it's something that we should obviously not do because it gives user space a look into what the kernel is doing, which we normally don't want to allow unless you are root. And the intended design here is to open the profile as root, which you can also do, and then you get to see which kernel functions are being called and so on. As you can see, they have names here and not just question marks, but the fact is the addresses are still here and they're visible to user space. And the way that we actually capture these stacks is kind of interesting and where the big problem lies. So, I mean, we shouldn't be giving user space these addresses to begin with, but I thought of something that makes this even worse, which is that this is just a stack walk. So we start at the current instruction pointer or the current frame pointer, and then we just walk backwards on the stack from where we are when we capture the sample. And these are all kernel stack frames, but here we jump out to user space, and the user space stack is writable memory in the user program, right? So we can actually modify that memory. And what if we would modify that memory so that suddenly we replace one of these stack frames with a pointer into the kernel? And then this thing that reads out the stack frame, that walks the stack to capture the full sample stack, it would just try to read the next stack frame from a kernel address. And there was this function that does this. So we have this thing called raw backtrace, which is a helper function in the performance event capture system, which is used by the profiling stuff. And you can see here that we have a SMAP disabler, and this guy is his job is basically to temporarily disable access restrictions that normally prevent the kernel from reading user space memory. But during the stack walk, we just completely turn off that protection mechanism. It's called SMAP because it's supervisor mode access prevention. Let me SMAP x86. Let me just bring that up. Yeah. So it's this thing right here. It's on by default. We just turn it off in a few small situations, including this one. So I think it should be possible to frick around with the stack here in the user space program and trick it into trying to read from a kernel address for one of these stack frames, and the whatever is at that address would then become the next entry in this list here. So since we're on 64-bit, we should be able to extract 64 bits of kernel memory from any arbitrary address by setting up the stack in such a way. So let's see if that's actually doable. So I found this bug last night, and then I went to sleep. So today we are going to see if we can actually make something out of it. So let's make a haxx CPP as usual. And let's get some of the basic stuff. So really what we're gonna need here is, I guess we need to be able to call profiling stuff. And we need to, the automatic profiling stuff that just captures events on a timer, it's not really ideal for this. But fortunately, we have a much sweeter mechanism called signposts. And I actually made a video about signposts when I was implementing them. And what they are is that they're just an API that allow you to generate a performance event that sort of says, oh, this thing happened, right? So for example, the JavaScript engine uses it to mark garbage collection events in profiles. And let's see if we just open a browser here, we can enable it for the PID of the web content process. Then maybe we do a garbage collection, a little bit of resizing, maybe another garbage collection. And then what we would get, oh shoot, I have to open it via the proc file system in this case. So just a sec, perf events, there we go. So we get these signposts event instead, one for each garbage collection in this case. And they also show up on the timeline here. So what is so neat about these is that we control exactly when they happen. So you can see that the garbage collection function in libjs calls a perf event API, and then that calls into the kernel. So this is very handy for what we want to do, because we just want to generate a perf event when we have set the stack up to look exactly like we want it to. So let's use that. Okay. So I guess we probably want to have a separate function here. So we'll do something like never inline go. Let's call it go. Okay. And what is go going to do? It's going to generate a perf event. Perf event signpost, sure. And then we have to pass in 2 integers. That might be enough actually. But before we actually do this, we have to screw up the stack frame pointers. So let's see. I guess we can just put a flat putter thing here, dummy, and then we have some global variable maybe like this, haxx address, haxx putter. We set that to the address of dummy. Haxx putter dummy, okay. And then at this point, we should be able to get to the relevant stack pointer address for the frame below us. let's see. So I'm not sure exactly how this will be laid out. So let me just print out a couple of addresses and we can see which one looks like the right one. So we'll print out the 8 nearest pointers on the stack or values on the stack, like this. So and maybe the content at that address as well. Okay, so I, and then haxx0ring minus I, let's say. Let's do this for simplicity. And haxx0ring minus I. Okay, and let's see what's actually there. It's been a while since I screwed around with stuff like this. So I'm gonna be a little bit rusty here. Okay. So we have let's see. So this is where the haxx0ring thingy starts out, and then the next thing, this looks like a, that's probably the return address, I would guess, because it looks ASLR'd. And this is probably the next stack address, I guess, because it looks like, so these are stack addresses. So like the next stack address would then be that one. So that's haxx0ring minus 2. Okay, so is this generating perf events? No, it's not. Oh, right, because we have to enable profiling in order for perf events to actually produce an output. So profiling enable, get PID. Oh, and then a mask of events. So we'll just say we only care about signpost events in this case. Let's see if that works. It doesn't even start. All right, so now we are producing a profile output, and it has one signpost event. And then we can actually look at these addresses here. We can see this guy right here, haxx0ring minus 1, is indeed the return address in main. So yeah, so then I think this one is going to be our target. So let's see what happens if we screw around with that thing, haxx0ring minus 2. So what if haxx0ring minus 2 is equal to, or assigned to, well, our kernel is at 0, 0, 0, 0, 20. I think that's the base address of the kernel base. Yeah, I'm just gonna copy that out and make sure that I get it right. And I guess this is probably gonna crash now because we're messing up the stack, but yes, it does. Yeah. So you get an NP fault because you are trying to read kernel address. That's kind of interesting. But what does the profile contain? Signposts. Okay, that was not terribly interesting. I guess we could actually print it out. because it's just a JSON thing. Okay, so first off, let's do this. Backup value is haxx0ring -2. And then let's even do this. Haxx0ref is haxx0ring 2. Okay. So with that, we should be able to not crash, I guess, because we are restoring the stack to the way that we found it. Okay, so everything is good. And then okay, so this is, I don't know how to read these numbers because they're not in hex, but we can always do this, this, this. Okay, so the stack actually looks just fine here. Maybe I'm screwing something up. I guess we can just insert debug statements here in the raw backtrace function. So we'll just print out as we go. So raw backtrace starting now. And then we will say see stack putter is this. And then we also want to print out the return address that we find at that stack pointer. So ret adder. These names could be better. They're a bit old school, like ret adder instead of return address. Let's see here. Okay, so what does this thing say? So this is nice. So we actually get a full trace through our stack walk here. And the thing that we were screwing around with was this guy right here. So FFC70, which is the stack pointer that we are reading from here, sure. And then the return address is this guy right here, which is stored at C78, not C70. Okay, is there a minus somewhere that I am missing or not thinking of? Stack putter plus size of flat putter. All right, so I need to account for that. Wait, hold on. This thing is all wrong. It was supposed to be -2, not 2. So let's try that again. Maybe I was misunderstanding the output. Let's see. So 3F0. We read from 3F0, and we get return address 69C9, which again is at -1. Oh, wait. I'm stupid. I just have to change that to -3. Yeah, the output is not going to look any different, but the thing I actually want to change is at -3, not at 2 or -2. So trying that again, and CF0, CF0. Wait, I'm still not doing this right. Oh, CC0, sorry. CC0. Okay, I'm not screwing this up correctly. Okay, so let me dump this out after I've done the mutation as well. Massaged. It's man, I feel like it's been forever since I was screwing around with this stuff, and it's so finicky. Like when you're more used to doing this type of stuff, it comes more naturally. But let's see, what am I screwing up? So this guy right here is who I'm changing. EF8 and EF8. I'm setting that one to the base of the kernel, sure. And then who are we reading here? E20. FF00. Oh, this thing. Okay. So we read that and get that. Did I just take a step in the wrong direction? Freaking offset math. Let's just try with -1 instead of -3. Plus, minus, left, right. So tricksy. Finally. Okay, that was the problem. I was going in the wrong direction. So now we can see that the kernel is reading from, or this is the return address. And previously, it picked up the correct return address. Now we're picking up the wrong return address. Good. But it's not the return address that we want to screw up, though. We want to screw up the we want to screw up the next stack pointer. So that would be like right next to it in memory, I would think. So this is -1, and it would be at -2. Wait. I'm just flailing around trying different numbers. All right, we got to get this right sometime. Oh, okay. Now we're getting it right. So look at this. So it's reading from these stack pointers that are all in the user space stack. And then finally, the last one it tries to read is the kernel base. That's now the final stack pointer. Okay, so after all of that confused back and forth with the offset, we're back to where we started, actually, with -2. So great. Should have just left it alone. But that is fantastic. So does that mean that what we're reading out here is actually the memory at the base of the kernel? Let's do something where we can learn something more. Let's get the address of some function. So let's just look at getUID. GetUID is one of my favorite functions. Okay, so here's the address of getUID. And then let's just add that to, to the base and see what happens if we try to read from getUID and Actually, I should have left that open. Get UID. So 49 BB blah 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 is the start of that thing, and please work. I mean, please work QEMU, not please work exploit. Okay, and it's reading from that address, and what do we have? 49BB00 blah blah blah. I don't see the right stuff. 090B94, or no, F090B9. F090B9. Okay, so we are a little bit off. Maybe we just have to, let's see. There's probably a little bit of offsetting here as well. I guess that's actually where I need to account for that pointer offset. So what I should be doing is -8, or size of void star, let's say. Okay, so get UID started with, wait, am I searching? 49BB. I feel like that was the thing. It's the start of this unrelated function, at least. Okay, get UID 49BB00 4C. All right, this is looking very promising. Okay, so let's say that can we capture more of these? I mean, I don't see why we couldn't. What if we just don't print out all this stuff? Okay, and ebdef, endif. All right. And then we do something like, and then how many reads do we want to make? So let's make like 32 reads. And oh, and now actually we want to actually get the thing from the generated profile as well. So let's see, let's first generate a bunch of these. So after each one, we can just do simple haxx0ring plus equals size of void. So we'll just advance by 1 pointer. And then do it again. And then afterwards, after all is said and done, we can open up the file. So we can open our own profile while we're still running. That's pretty neat, actually. So we'll just get libcore file. We'll get the JSON parser stuff. And let's see, auto file is core file open string formatted proc mypid perf events. I'm just going to open that read only. And we assume that it works because this is just a silly exploit. We don't need to be super careful about error handling here. So we'll just crash if it has an error. And then the JSON is going to be, let's do JSON value from string file read all release value. Okay. Now, what we have here is going to be something like this thing, like this guy right here, just a JSON encoded profile events stream. So we want to, how does this thing start actually? Can we pipe to less? So we want to look in the events array. So events is JSON as object get putter events. Sure. And then we want to walk this array and look for events of type signpost. So event in events value. Wait, that's an array, so we can turn it into an array. Yes, yes, yes. All right, here we go. Event as object get type. If it's not signpost, continue. But if it is signpost, to string, yeah. Oh man, all of this stuff is unfamiliar almost, like it's been so long. But how fun is this? So let's see. And then we just want to look in the stack array of this guy right here. So he has a stack is event as object get putter stack as array. And then I guess it's going to be the very last entry. So 0, 1, 2, 3, 4, 5, 6, entry number 6. Because if we accidentally read some part of memory that happens to be a valid kernel pointer, then what will happen is we might get more frames. Or if it's a valid kernel or user space pointer, we'll just get more frames basically. But frame 6 there should always be the one that we want. Haxed value is stack at 6 to U64, or do we have to number flat putter? Yes, that's what we want. Okay. And now we can print out the haxed value. And let's see if this works. So we should now be reading out 32 pointer size values starting at the entry of getUID in the kernel, and then printing them out on screen. Okay. And they are, I think it worked actually, but they're backwards, right? So you have to read from here to there to there. We can improve that. So let's just do something really ugly, like like something like this. 1, 2, 3, 4. 1, 2, 3, 4. Wait, that's too many numbers. What am I doing? Yes, that should be enough. And then the first one is going to be just and ff. And then we have haxed value. Let's see. Okay, something like this. And then let's do a little bit of this good shit right here. Okay. So will that do the trick? Okay, does this match get UID? Let's double check here. So 49BB04C, sure. And then starting at, or I guess we don't have start addresses here, but it continues 5548B9. That's 5548B9. Yeah, so this thing is basically working. So what have we done here? We have massaged the user space stack so that one of the stack frames, the stack frame that called us, actually looks like it is a stack pointer inside of the kernel. And when the perf event syscall tries to capture the stack that called the perf event generator, it just happily walks the stack and reads that kernel address, like thinking it's just another stack pointer. So that is not super good because it allows us to extract arbitrary kernel memory just like this. And yeah, so I think basically this should allow us to extract the entire memory space of the entire system, actually, of the current process and everything in the kernel. Of course, we can't immediately access the memory space of other processes, but an arbitrary read of all kernel memory that it has the additional benefit of not crashing if you do a bad read, because it's using safe memcopy here, which if a fault happens while you're reading, we'll just swallow the fault and stop walking the stack at that point, but we won't crash the system or anything. So this is a really like resilient arbitrary memory read. Not super good. So I don't know that I could immediately turn this into a privilege escalation like in some obvious way. There's probably all kinds of non-obvious ways of leveraging this powerful vulnerability into privilege escalation, but nothing. I feel like I would need some kind of write primitive in order to do something more interesting, and I don't have that. So I think we'll be happy with this here for today. But of course, now we have to do something about this as well. So the first thing that comes to mind is that we should definitely filter kernel addresses when we are dumping out this JSON. So we have this to.json thing in performance event buffer. And here at the moment, we are just like happily letting out these addresses, whatever they are. So where are the stacks? I guess here, yeah, stack array. So I think what we're gonna do here, we have this thing called dead code that we use in the proc file system. If you're trying to look at something that has kernel addresses in a proc pid stacks file. No, what's the thing? Stacks. Wait, why didn't that glob work? That's weird. Anyway. Yeah, so this is the stack of the current program, and it should turn any kernel address into hex dead code if you are not the super user. So I think we can do the same thing when we dump out performance events into a JSON stream, because then if you are root and you try to read a performance event stream, you get kernel addresses. If you're not root, you don't get them. I think that would be a nice safeguard against this thing. So like, let's see. So if, what was this thing doing? If show kernel addresses, and then if kernel address added continue. Let's see. So show kernel addresses is process current is super user. So let's borrow that because that looks nice. Okay, and then say auto address is the address, else if not show kernel address, and memory manager. No, what's the API? Is kernel address? What was that thing using? Is user address. Okay. Is user address virtual address. So we just check if it's not a user address, then we set it to dead code. Okay, so let's see if that is, that should disable the exploit, I think, because we should just, or wait, will it? I don't think it will, because this isn't, the snuck out value is not actually necessarily not user address, but it ends up working anyway. Okay, let's see. Because now we just get dead code, sure. But why does that work? I think it just works because the byte streams that we get from the getUID code also doesn't look like user addresses. So it's a start, but actually there are a bunch of protections we should have here. Like we also shouldn't allow non-root users to even see these events like kmalloc and kfree, because those are kernel events. So maybe we should have more like a filter for those even earlier. Let's see. Show kernel addresses. If not show kernel addresses, if event type is, so if it's kmalloc or kfree, then I don't want to. You don't want to show those either. And there's probably more restrictions that we could put in place, but that one just seems kind of obvious. So raw backtrace. I guess the main problem is that we have been in the kernel once in our stack backtrace, or like in our stack walk, and then we have exited the kernel, started going through the user space stack, and then we're going back into the kernel again. And that should never naturally happen. Like there shouldn't be a situation where we call the kernel and then the kernel calls back to us and then we call into the kernel again. That's sort of a bogus stack state. So I think we can probably just check for that. Is that what that other thing already does? Kernel address added. If not, wait, what is it doing? Kernel address added. So just, oh, I see. So this is just coalescing them into a single dead code. That's fine, I guess. But I just want to stop walking in case I encounter a kernel address after having one. So let's see. We would have something like has left kernel stack, has traversed has reached end of has reached, let's say it has to reach end of kernel stack for now. So it starts out with false, and then if stack putter, if that's not a user address, so the stack pointer is not a user address. Now we're in the kernel. So if has reached end of the kernel stack. Okay, let's call this something else. Has is in users, is walking user space stack. So that's where we stop. Yeah, so we break the walk here. Shenanigans. User space stack walk, stack points back into kernel memory. Yeah, that is a straight up shenanigans situation. So let's see. Otherwise, is walking user space stack is true. Yes, so it's fine to walk the user space stack as long as you remain in the user space stack. Let's see how that works out, because that should break the backtrace mechanism. So we're getting 2 layers of protection here, which seems like a good thing. Let's just verify that this actually stops the stack walk. Shenanigans. And then haxx fails because we don't get the right number of stack frames, of course, in the JSON. Yeah, so shenanigans. User space stack points back into kernel memory. That is a nice thing to stop. So very good. Okay. Yes. And there might be more places that do stack walks that I have to track down and fix this as well, but I'm not gonna look for all of those in this video because I want to kind of wrap it up. But I think we have some nice fixes here. So let's see which one we do first. Put a note here. Note. The kernel never. Once we have walked. No, wait. The stack should always have kernel frames first, followed by user space frames. If a user space frame points back into kernel memory, something is afoot. Yeah. Okay, so let's do that one first. Kernel. Let's see, stop perf event stack walk on bogus user space kernel traversal. When walking the stack to generate a perf event sample, we now check if a user space stack frame points back into the kernel, back into kernel memory for this this was exploitable as an arbitrary, let's say it was possible to use this as an arbitrary kernel memory read. Yes, good. Okay, and then let's filter out the kmalloc and kfree events for non-super users. Kernel don't include kmalloc, kfree, perf events in JSON for non-super user. Let's just say kmalloc perf events, yeah. Yes. These events contain sensitive kernel information and should not be available to regular users. Indeed. And then we also filter out kernel addresses to dead code in the output stream. So kernel mask kernel addresses in perf event streams for non-super user. Now turn kernel addresses into 0x dead code, same as proc it stacks. Yes, I am sure that there are more issues like this and I need to track those down. And I would invite other people to help me track those down as well. But I think we have managed to make some nice improvements here. And it was pretty sweet to get that exploit working. So let's just verify that it no longer works. Haxx. Well, it just, of course, it crashes when we try to read it. Let's delete all those things also. Okay, did that give us a profile? haxx0ring. We have all these signposts. They still have kernel addresses in them. Uh-oh. All right, that's not good. Why are they still there? haxx0ring, why? What did we miss? I did something wrong. Okay, what did we do wrong? Walking the stack. Show. So if not show kernel addresses and not is user address. Okay, I guess we can do something like this. Is user address for P? And then we just say what it tells us. Because maybe something is going wrong here. Okay. All right, come on now. Yeah, there's something that goes wrong at boot sometimes when Windows Server doesn't come up properly. I don't know what that is. Happens every couple of boots. All right, so is user address, blah, blah, blah. So these are false. So they should not be included in the output. But Looks like they are though. So why is that? Guess we will have to show. Maybe my logic is totally bogus. Current is super user. Oh, wait. This is the perf core, actually. So, okay, so what I'm looking at here is not, I'm not accessing the perf events through the proc file system, but I'm actually, you get this dump after the fact, like after a program exits. If it had unreported performance events or recorded performance events, then it will dump out a file with all of that stuff. And that thing will have, that thing is being generated as a root. So, that's not super great. What would be a good behavior for that? Maybe the right thing to do is to make the obvious easy fix for this right now is to generate those as read-only owned by root. So that's definitely an option. So I think maybe that's what we'll do, because like it's still really useful if you get one of these and then you can open it up as root and see like the full perf event stream, including kernel stuff. And I don't know how we would make that like ergonomic otherwise. So let's do that with some kind of perf core thing. Perf core file name. And yeah, so they're generated with UID, GID of the current process, but let's just put 0, 0 here for now. I think that will that patches up this issue, although I don't love it, but like I think it's still better than nothing. As long as you own the directory, you can delete the thing. And then I don't know exactly what would be the most ergonomic thing we can do about this. If anybody has suggestions, I would be very happy to hear about them. But yeah, so now we get one that's owned by root, and of course I can't open that. But if I'm root, I can open it up, see all the signposts. So I think that's okay. Yeah, for now, that's a decent fix for that. Kernel, save for perf core files. Make perf core files owned by UID 0 gate 0. Since perf core files are generated by can be generated during process finalization, we can't just allow them to contain sensitive kernel information. If they're gonna be owned by the process's own UID plus GID. So instead, perf cores now owned by 0, 0. This is not the most ergonomic solution, but not sure what we could do to make it nicer. We'll have to think more about that. In the meantime, this patches up a kernel info leak. So yeah, so there we go. Whole bunch of tightening fixes for performance events and perf course and stuff. So very, very good stuff. I am quite happy with these changes so far. And I'm sure that, as I said, I'm sure we have more bugs like this, but we just have to go day by day and find them all. And before I end the video, I definitely want to show you that I have upgraded the Serenity OS bug bounty program. So I used to pay $5 for exploitable bugs in these categories following these rules, but I have upped the reward to $50. I thought it was time to do that because I have better funding these days. I get a lot more contributions or donations on GitHub sponsors, Patreon, and PayPal than I did when I first set up the program. So I wanted to increase this to better reflect how the project is growing, and also to make the rewards scary again for myself. It is a little bit scary to offer this much, and when I originally announced that I would pay $5 for bugs, that was scary to me then, because I thought, well, what if somebody finds a lot of bugs? And then over time, like $5 became less scary. $50 is once again scary. So it would be great if people would find security bugs in the system. So read more about the program at serenityos.org/bounty if you are interested in hunting down security bugs and getting some sweet bragging rights and a $50 reward. So this has been our first haxx0ring video in a while, but I thought it was really interesting, really fun to do. And I did feel a bit rusty, but we ended up with a working exploit and a reasonable security fix or set of security fixes. So I think that's good. So this will be the end of today's video. So if you made it this far, then I thank you for watching, for hanging out. I hope that you saw something interesting here and maybe got a little bit interested in doing security work yourself of some type. Yeah, I will see you all next time. Bye.